Before we explore the details of wastewater treatment plants for resins, let's take a moment to understand the significance of treating waste such as unsaturated polyester resin and alkyd resins roughly. Unsaturated polyester resin and alkyd resins are pivotal synthetic polymers widely used in industries. UPR excels in strength and corrosion resistance for composite materials, while alkyd resins offer adhesion and durability for paints. Their production involves meticulous processes and the addition of various additives to customize properties. In light of significant environmental and health risks posed by the excessive production of alkyd resin and UPR, proper waste disposal becomes a critical challenge due to the hazardous components. Incorrect handling may lead to soil and water contamination, threatening health concerns. As both UPR and alkyd resins are classified as hazardous waste, strict compliance with handling regulation is vital. A comprehensive approach is required, including recycling, alternative materials, and sustainable formulations. Wastewater treatment emerged as the optimal solution aligning with regulatory standards and demonstrating a commitment to responsible waste management, ecosystem protection, and human health.
I will continue with the process production of unsaturated polyester resin and alkyd resin. In the UPR production process, raw materials undergo polymerization in a reactor with agitation followed by mixing in a blender. Adjustments are made in an adjuster tank and pixel tank. Heat generated is managed by a partial condenser and volatile components separated in a total condenser. The UPR then undergoes filtration for quality control before storage in a receiver. The final product is packaged for distribution. VOC scrubber is used to capture volatile organic compounds and chimney for safe release. Liquid byproducts are treated in wastewater tank and scrubber wastewater is managed responsibly in a separated tank. While in alkyd resin production, raw materials like vegetable oils, xylene, and pentatritol along with catalysts are mixed in a reactor. Unlike UPR, there's no need for adjuster or pixel tanks. Xylene is separated using a decanter and recycled back to the reactor. From the production process of UPR and alkyd resin, waste generation includes solid, gas, and liquid waste. Solid waste comprise resin dust and particles generated during handling and processing, as well as packaging materials used for raw materials intermediates, final products, and byproducts. Biomass waste includes organic materials like wood, leaves, or plant debris generated during construction. For gas waste, arises from gases emissions produced by solvents and monomers, contributing to air pollution. Leftover chemicals such as styrene and phthalic anhydride, which didn't fully participate in production, may be toxic and require careful handling. Liquid waste streams may contain unreacted raw materials, intermediates, byproducts, and impurities. Wastewater from cleaning and maintenance processes contain solvent, detergents, and other cleaning agents. From waste generation, various adverse impacts on the environment and human health arise. Primarily, volatile organic compounds (VOCs) released during resin production contribute to air pollution. These VOCs can react with other pollutants, leading to the formation of ground-level ozone and smoke. For improper disposal or management of solid waste, such as resin, dust, and byproducts, can contaminate soil, impacting its quality and potentially harming nearby plants and organisms. Liquid waste discharged, including untreated processed effluents and wastewater from cleaning operations, can pollute water bodies. This pollution affects aquatic ecosystems and may pose risks to human health through water consumption or contact. To maintain control over plant pollution, various laws and regulations have been established. These regulations primarily aim to monitor pollutant and wastewater quantities, ensuring they remain within specified limit. Strict adherence to these laws and regulations is obligatory without exceptions. Our manufacturing facility is required to comply with the Environmental Quality Act (EQA) of 1974, along with supplementary regulations such as the Environmental Quality Industrial Effluent Regulations 2009, Environmental Quality Clean Air Regulations 2014, Environmental Quality Scheduled Waste Regulation 2005, and Environmental Quality Sewage Regulation 2009. Additionally, strict adherence to the Clean Air Regulations of 2014 is also mandatory for our facilities.
So how to achieve zero effluent by thermal oxidizer? First of all, let us go through what is thermal oxidizer all about. Thermal oxidizer is a combustion device that reduces air pollution by eliminating hazardous air pollution, volatile organic compounds, and other emissions produced by industrial activities. This device converts hydrocarbon-based pollutant into carbon dioxide and water before emitting them into the thermal oxidizer. So now, let's look on the working principle of thermal oxidizer by following each number in the figure. At point number 1, the pollutant is forced through the oxidizer by a system fan. If the process air stream does not contain enough oxygen for burning, ambient air is introduced. This is crucial for the oxidation process, where the pollutants react with oxygen to produce carbon dioxide and water. Next, at point 2, the air flows via a heat exchanger to warm it before entering the combustion chamber. The chamber is designed to provide the right condition for complete combustion, including the proper temperature, residence time, and turbulence. In order to guarantee the complete elimination of volatile organic compounds, the air in the combustion chamber is heated to a high enough temperature and maintained there with turbulence reach point at point 3. As a result, the VOC burns to produce carbon dioxide and hydrogen. After that, at point 4, through the heat exchanger's hot pass, the hot and clean air continues by capture and utilize the heat generated during combustion. This can be used to preheat the incoming air or other process stream, improving overall energy efficiency. And lastly, the clean air is thereafter released into the atmosphere through stack or exhaust vent at point 5. Move on to the operating condition of thermal oxidizer. The operating parameters of a thermal oxidizer are critical for the efficient and successful treatment. The operating parameters may differ based on the type of thermal oxidizer. Temperature, pressure, air flow rate, residence duration, purge and inert gas system, and heat recovery are examples of frequent operating conditions. Firstly, temperature. Thermal oxidizer use high temperature to aid in the burning of contaminants. Typical operating temperatures range between 800 and 1200 degrees C. For the pressure, thermal oxidizers are typically operated at approximately atmospheric pressure. However, the pressure can vary slightly based on the design and uses. To maintain the ideal air-to-fuel ratio for combustion, the air flow rate of the entering process stream and combustion air are precisely regulated depending on the process. And for the residence duration, typically the residence time spans between 0.5 and 2 seconds for thermal oxidizer to function. Purge and inert gas system are sometimes included with thermal oxidizer in order to regulate the combustion chamber's environment. Certain gases can be utilized to manage the combustion process, whereas inert gases can help remove any explosive or flammable gases. Lastly, heat recovery systems are designed to collect and apply the heat produced during combustion to preheat process stream or incoming air.
Continuing the presentation, I will describe the implementation of the existing thermal oxidizer system as to treat wastewater coming from alkyd resin process and also the unsaturated polyester resin process. The process diagram describe a total of 7 equipments ranging from pump, the main equipment combustion chamber, the thermal oil heat exchanger, the air cooler heat exchanger, the stack, and also the discharge duct. Accompanying those equipments are the 12 streams that represent the inlet and outlet flow of the thermal oxidizing system. The treatment of the wastewater from alkyd resin process and also the unsaturated polyester resin process will begin as the inflow of the untreated wastewater combustion booster, which is the natural gas, and also the fuel source coming from UPR and alkyd resin production. So the waste produced, the combustion booster and also the fuel source, which is the natural gas, will enter through stream 2, stream 3 and stream 4 with an additional stream of preheated combusted air through stream 1. These waste streams that are coming from different stages of the resin production processes get collected and directly funneled into the thermal oxidizer as to be treated in the combustion chamber by breaking down the components of the volatile organic compounds and also the hazardous air pollutants. In the combustion chamber, a high temperature zone is set at 1000 degrees Celsius that is maintained by the sourced in fuel, which is the natural gas. So in the combustion chamber, the organic compounds are thermally composed and get turned into harmless byproducts, which are carbon dioxide and water vapor. The waste stream will usually retain within the chamber for this sufficient amount of time, typically around 0.5 to 2 seconds, in ensuring the complete oxidation and destruction of volatile organic compounds and hazardous air pollutants. So following that, after the gases byproduct has been produced from the VOCs and the HAPs, the waste stream will exit the combustion chamber through stream 5 prior entering the heat recovery phase, whereby the incoming waste get preheated by the high temperature exhaust gas coming from the combustion chamber, utilizing an overall cyclic energy distribution. So the gases byproduct will proceed through stack comprised of scrubber and baghouse to remove any remaining particulates and acidic gases before they are released to the atmosphere.
The utilization of backup wastewater treatment equipment, particularly through Integrated Environmental Treatment System (IETS), offers several impactful benefits for the environment. Firstly, backup wastewater treatment equipment often incorporating advanced technologies, optimize water and chemical usage, fostering a sustainable and responsible approach to water usage and mitigating environmental impacts. Additionally, IETS can significantly enhance pollutant removal, minimizing potential adverse effects on ecosystems and safeguarding public health. The efficiency of pollutant removal directly contributes to the environmental integrity of treated water. Furthermore, wastewater treatment systems prioritize energy efficiency as a key component of their design. Technologies such as membrane bioreactors, aerobic digestions, and innovative chemical treatments are more energy efficient compared to conventional methods.
Wastewater treatment has grown important as a source of nutrients, energy, and clean water. So sustainable IETS should aim to optimize resource utilization, minimize the use of chemicals, water, and other sources. Recycling and reusing treated water can also enhance sustainability of the wastewater treatment process. Besides, IETS often incorporated with multiple treatment stages such as physical, chemical, and biological processes, which leads to more comprehensive pollutant removal. So lastly, the energy efficiency of IETS plays a crucial role in the environmental sustainability. Technologies that prioritize energy efficiency and utilize renewable energy sources can minimize the overall carbon footprint associated with wastewater treatment.
When considering a backup wastewater treatment plant, an evaluation is essential to guarantee effective treatment during primary system failures or emergencies. Critical factors such as wastewater type and characteristics are examined across economic, environmental, and social dimensions. The decision-making process for wastewater treatment involves a comprehensive assessment of three distinct methods: IETS, Industrial Effluent Treatment System, Electro-oxidation of resins, and AOP, Advanced Oxidation Process. IETS is a comprehensive approach to treat industrial wastewater involving physical, chemical, and biological processes to remove pollutants. It aims to meet environmental discharge standards and minimize the environmental impact of industrial effluents. Electro-oxidation of resins utilize electrochemical reactions to break down and remove contaminants from wastewater. This method is effective in treating complex industrial effluents containing organic pollutants. AOP, Advanced Oxidation Process, involves the generation of highly reactive hydroxy radicals to oxidize and degrade organic, as well as inorganic pollutants in water. AOP are known for their versatility and effectiveness in treating a wide range of contaminants, making them suitable for diverse industrial wastewater treatment applications. Each of these methods offers unique advantages, and the selection depends on the specific characteristics of the wastewater and the desired treatment outcomes. As we delve into the wastewater treatment plant for resins, it is crucial to understand our scoring methodology. This structured evaluation system assesses the efficiency, environmental impact, and regulatory adherence within three wastewater treatment processes. We consider factors like equipment, operational costs, complexity, removal efficiency, compliance, technological innovation, environmental impact, and safety measures. Scoring method assigns specified marks to each criteria for the backup wastewater treatment process of alkyd resins and UPR. This approach ensures a comprehensive and also systematic evaluation of their performance. According to the scoring method outlined in this table, IETS, Industrial Effluent Treatment System, outperformed Advanced Oxidation Process AOP and Electro-Oxidation of Resins by achieving higher score across the specified criteria. This emphasized the superior performance of IETS in this evaluation, as it demonstrates more advantages than disadvantages when compared to the other processes. The strengths of IETS stand out, positioning it as a favorable choice in our wastewater treatment considerations.
In search of substitution of the existing thermal oxidizer system, we proceed with the Industrial Effluent Treatment System IETS, as it scores the highest amongst other available processes, which are the electro-oxidation of resins and also the advanced oxidation process. The IETS are outlined here, having multiple equipments ranging from fine screen, equalization tank, coagulation and flocculation tank, primary resettling tank, aeration tank, secondary clarifier, and also the sludge holding tank. Note that the description of the treatment equipment are sequential because the treatment will take place sequentially, whereby it enters from the fine screening and being flown out as the effluent, which is the treated wastewater, and also the sludge through secondary clarifier and sludge holding tank. To fully understand the mechanism of the IETS in handling the wastewater coming from the manufacturing of alkyd resin and unsaturated polyester resin, so the sequential steps being described earlier are further undergo detailed description, whereby the commencement of the wastewater treatment begin with screening to eliminate larger solid particles and debris. Following this, the primary treatment phase incorporates customized physical and chemical processes specific to the characteristic of alkyd resin and unsaturated polyester resin effluents. We can see that there are a few adoption of biological and physical treatment being incorporated in the IETS as to treat the wastewater, because presence of VOCs and HAPs resulting in the high concentration of BOD and COD. So the primary treatment involves the settling of the heavier solid that present in the wastewater at equalization tank. Following that, the further treatment will be using chemical agents, whereby to bind the chemical in order to aggregate fine suspected solids, facilitating the removal by sedimentation earlier in the equalization tank. The partially treated water then proceed to a primary settling tank to remove any physical material that are present in the wastewater, whereby solid particles are being removed from liquid phase wastewater. So secondary treatment, whereby involves the use of biological processes, introduces the use of aeration tank, whereby it is essentially a swimming pool for microbes, but with a crucial twist, whereby the oxygen bubbles constantly being sourced in the tank throughout the water, and continuous aeration provide oxygen for the microorganism to thrive on the oxygen to be well fed for the vital element, enabling them to do their job in breaking down the organic pollutants. So think of the aeration tank as a microscopic buffet. So the wastewater are the tasty treats whereby the resident microbes are the eager diners. So the wastewater flows through the tank. As the wastewater flows through the tank, the microorganism gobble up and decompose the organic matter, transforming it into simpler, less harmful substances like water and carbon dioxide. So the biological breakdown significantly reduces the organic load, paving the way for the cleaner water. However, we still incorporate the use of secondary clarifier because further final settling of the wastewater need to be done for the wastewater to be discharged accordingly with the compliance of the environmental standards, minimizes the environmental impact, and also to promote responsible and sustainable wastewater management practices.
The main purpose of using thermal oxidizer is to eliminate harmful pollutants and reduce air pollution. However, thermal oxidizer can also give negative impacts on the environment based on few reasons. First of all, the usage of thermal oxidizer in the waste management industry to treat exhaust gases generated during the processing of waste materials produces carbon dioxide and water vapor. Although the produced carbon dioxide and water vapor are not harmful, the releases of carbon dioxide into the greenhouse effect and climate change. Next, the high temperature used in thermal oxidizer can lead to the formation of nitrogen oxides, which can contribute to smoke formation and acid rain. The combustion related to nitrogen oxides and sulfur oxides can damage plants and animals. Last but not least, the thermal oxidizer operates at high range temperature. It requires high energy for operation. The combustion process involves the system consumes fuel or electricity, which also contributes to the greenhouse effect and climate change. The sustainability of thermal oxidizer in industrial applications is a critical consideration as industries seek effective solutions for managing emissions and environmental impact. Emission reduction from thermal oxidizer is designed to reduce emissions of volatile organic compounds and hazardous air pollutants. The harmful pollutants are broken down into simpler, less harmful substances, including carbon dioxide and water, during the oxidation process. Other than that, when the usage of thermal oxidizer is with compliance with regulations and standards, greenhouse gases emissions can be controlled and reduced. By meeting the regulatory standards set by the government, companies could contribute to overall reduce harmful emissions and mitigate their impact on the environment. Lastly, the implementation of energy efficient systems and technologies will help with the minimization of the overall environmental footprint associated with energy consumption. Moreover, heat recovery systems are a common feature of contemporary thermal oxidizer, which collects and repurposing the heat produced by burning fuel.
Next, in designing an equipment, two major parameters is used, which are calculation of mass balance, then design the equipment. In the mass balance, the calculation generally use equation below, which is mass out equal to 1 minus percent of removal times with mass into the system. Based on Environmentally Quality Act EQA 2009 of Department of Environment DOE, the requirement for compliance effluent wastewater is follow standard B. Table here shows the parameter in standard B that need to be complied with, where DOD should less than or equal to 50, COD should less than or equal to 200, TSS should less than or equal to 100, and the pH value is around 5.5 until 9. Based on the information obtained, wastewater produces in the UPR and AR production is 3,717.7 kg per day, while the influent wastewater to the thermal oxidizer is 825 kg per hour. So, for the calculation of mass balance, the flow rate of the wastewater entering the IETS is assumed to be 4,000 kg per hour. The data of DOD, COD, TSS, and pH value in the wastewater is collected from resin industries. Table here shows the parameter and its value obtained, where BOD is 5,600 mg per liter, COD is 16,300 mg per liter, TSS is 1050 mg per liter and the pH value is 3. The summarization parameter and its value is shown in the table here. Since several parameter value in this production plant does not comply with Regulation 3 of IER 2009, the wastewater meets the requirement to install IETS. A mass balance calculation for each unit operation within the IETS will be based on the assumption provided. In IETS, we use 6 equipments for wastewater treatment in order to get parameter value that comply with standard P. Firstly, the wastewater will undergo screening process where this equipment can remove 35% of the TSS. Next, it will enter equalization tank with both BOD and COD can be removed by 30%. Then, it will entering coagulation and flocculation tank with removal efficiency of BOD and COD value is 55% and 65% respectively. Next, the wastewater will entering primary settling tank where it can remove 60% of BOD and TSS and 40% of COD. The fourth equipment is the aeration tank. Here, the removal efficiency of BOD, COD and TSS are 75%, 33% and 83.5% respectively. And lastly, the treatment continues at secondary clarifier where here the clarifier can have removal efficiency of 94% of BOD, 97% of COD, and 84% of TSS. The summarization table of effluent is compared with the value fixed in Standard P by Department of Environment DOE. The value of BOD, COD, and TSS is 10.58, 48.16, and 7.26 mg per liter, where it is less than the Standard B indicator. Since all the final value in each parameter is less than the value of Standard B, it can be said that the effluent discharge is compliant.
For the design and sizing of the equipment, a few assumptions have been made. For fine screening, we assumed that the effluent discharge is 4,000 kilograms per hour, which is 96 meter cube per day. The bar width, bar depth, and clear spacing between bars are 15 mm, 40 mm, and 30 degrees respectively. Next, moving on to the equalization tank and coagulation tank, the water depth is assumed to be 5 meter. With a square design, the length and width will be equal to each other. The detention time at the equalization tank was taken at 2.5 hours, while the design factor of the coagulation tank is 2 and detention time is 3 minutes. The design factor for flocculation tank is the same as coagulation tank, which is 2, while the detention time is 40 minutes. Next, for the primary settling tank, the surface overflow rate is assumed to be 35 meter cube over meter squared per day. The design factor for aeration tank and secondary clarifier are both 2, and the yield coefficient for aeration tank is 0.8, while secondary clarifier is 0.9. For the sludge age, we assumed for 15 days at aeration tank and 10 days for second clarifier. The table shows a summary of the sizing for the equipment involved in the IETS wastewater treatment system.
In conclusion, the main reliance is on a thermal oxidizer procedure and precise a dedication to effectively neutralizing VOC, hence reducing the ecological consequences of industrial waste from both UPR and AR production. The selected process by using an industrial effluent treatment system IETS as a backup solution demonstrates a proactive contingency strategy where it is a dynamic and adaptable wastewater treatment plant that guarantees resilience and continuity in the event of unforeseen operational disturbance. The calculation for mass balance of the IETS process is carefully made by considering BOD, COD, and TSS. These parameters are crucial when it comes to designing an IETS since the target is to get the value that is compliant with the wastewater standard fixed by DOE. Next, the design and calculation for every equipment is integrated strategy that makes a proactive approach to safely managing industrial waste. In the case of a waste treatment malfunction, what should we do? Here are some recommendations if the treatment system fails based on NHDES, wastewater engineering operation, and maintenance manual emergency response planning. Firstly, we can do emergency shutdown. It is recommended to conduct an emergency shutdown of the waste treatment system in order to stop the flow of waste and avoid future problems. For example, select an emergency shutdown coordinator that is well-trained to manage the shutdown procedure. Secondly, isolate the system. Isolating the defective part of the system is critical to prevent the spread of any dangerous contaminants. For example, turn off utilities that power the waste treatment system, such as electricity, gasoline, and other energy sources. And thirdly, provide medical assistance and emergency first aid. For example, set up first aid station with the appropriate medical supplies. Aside from that, arrange local emergency medical services and plan transportation to medical center. This approach enables a complete waste to protect individuals' health and safely during waste treatment outage. So that's all from us. Thank you.